Welcome to the deep dive. Today we're tackling something that sounds, well, pretty complex. The quantum vortex. It's fundamental to quantum mechanics, though. Our mission is to unpack these mysterious quantum whirlpools. We want to figure out what they are, where you find them, and why physicists have been so interested for decades. Going back to early predictions from people like Lars Onsager, London, then Feynman and Abrikosov with superconductors. So let's dive right in. What is a quantum vortex, fundamentally? I've heard it described as a quantized flux circulation, sort of like a tiny, super-ordered whirlpool, and maybe a kind of topological defect.
Yeah.
What does that mean, and where do we actually see them?
Yeah, that's a good start. They are essentially these highly structured whirlpools at the quantum level. And you're right, they are a type of topological defect, meaning they're stable structures kind of woven into the fabric of the quantum state. You mainly find them in some pretty extreme conditions. Think superfluid.
Like liquid helium.
Exactly, liquid helium or Bose-Einstein condensates. And also, crucially, in superconductors. They're often called Abrikosov vortices, but they even pop up elsewhere, like in photon fields, optical vortices, and these things called excitant polariton superfluids.
Wow, okay, so helium, superconductors, even light. That's quite a range. What's the common thread there?
Yeah.
And you mentioned quantized. That word sounds really specific, very quantum. Can you break down what quantized actually means for these vortices? Why is that so important?
That's really the heart of it. Quantized here means the circulation, the sort of spin speed around the vortex can't just be any value. It has to come in specific, discrete steps, integer multiples usually.
Okay, like steps on a ladder, not a smooth ramp.
Precisely. Think about the quantum state, like in a superfluid, as a wave. For that wave to be stable as it goes around the vortex core, its phase, sort of its position in the wave cycle, has to perfectly match up with itself after one full rotation. This constraint forces the circulation into those fixed steps. It's like a tiny whirlpool carrying a specific set amount of angular momentum.
I see. And how does that play out in superconductors? You mentioned the Meissner effect, where they usually push out magnetic fields.
Right. So superconductors normally expel all magnetic fields,
Right.
but in what we call type 2 superconductors, it's actually energetically cheaper for them to allow magnetism through in tiny controlled channels. Those channels are the quantum vortices. Each one carries a precisely quantized amount of magnetic flux. It's closely related to earlier ideas by London on magnetic flux quantization.
Fascinating. And this isn't just about these exotic materials, is it? The idea pops up in theoretical physics, too.
Oh, absolutely. It's used in frameworks like the de Broglie-Bohm theory. Their vortices are basically points where the quantum wave function goes to zero and you get this sort of swirling flow pattern around them.
Yeah.
And thinking about applications, we also see constrained vortices in magnetic materials, ferromagnets, antiferromagnets.
How does that work?
Well, the properties of these tiny magnetic whirlpools, like their direction of rotation or the polarization of their core, can actually be switched. This means you could potentially use them to store information, not just 0 or 1, but maybe 4 states by combining rotation and polarization. Imagine the potential for really dense data storage.
That could be huge for future tech. Okay, now, for something that sounds really counterintuitive, Onsager predicted negative temperatures from these vortices. How is that even possible? Temperature usually stops at absolute zero, right?
It is truly mind-bending. Onsager figured this out way back in 1949, theoretically. He saw that if you have just a collection of these point vortices isolated, their statistical mechanics could lead to a negative Boltzmann temperature. And it's not just theory. It was actually seen experimentally in 2019 in a Bose-Einstein condensate.
Wow. So what does negative temperature mean? Is it colder than absolute zero?
Not quite colder. It's actually hotter than infinite temperature, in a way. Think about it like this. Normally, adding energy increases temperature. But in these specific systems, the highest energy states are actually the most common ones. So if you add more energy to a system already at effectively infinite temperature, it pushes it into this negative temperature regime where adding energy decreases the entropy. It completely flips our usual thermodynamic intuition.
Okay, I think I need a moment to wrap my head around being hotter than infinity. That's something else. And thinking about how these vortices come about, they don't always have to be deliberately created, right? They can form spontaneously.
Exactly, yeah. That relates to something called the Kibble-Zurek mechanism. Imagine you cool a substance down really fast to form a condensate. Different regions might start ordering independently with different phases. When these regions merge, the boundaries, the mismatches, can trap defects, and those defects can be quantum vortices. We actually observed this happening in atomic Bose-Einstein condensates back in 2008. They just appear as the system orders itself.
So this deep dive really highlights how quantum vortices are this incredible link between fundamental quantum rules and things we can actually observe and measure, from tiny whirlpools in helium to potential data bits and even forcing us to rethink basic concepts like temperature. It's amazing stuff. So for you listening, think about this. These quantized whirlpools dreamed up decades ago are still driving new discoveries. They could be key to future quantum computers, maybe new materials, or even help us understand the most extreme parts of the universe. It shows that sometimes exploring these really strange quantum effects is where the biggest breakthroughs lie.